If you cannot sleep, let this device become a quiet observatory window. Tonight, 8 riddles become gentle measurements, one mystery at a time. Soon you will hear how a faint radio hush supported the Big Bang. Tap Save, lower your screen brightness, and let the volume sit just above a whisper. When you wake, comment A for sleep, B for focus, or C for quiet learning. Let's set a quiet roadmap so your mind can stop scanning for surprises. Everything tonight follows the same gentle pattern, like footsteps on a familiar path. First comes a simple question, asked in plain language. Then we notice a clue, often something small that repeats in the data. After that, we meet the breakthrough when a tool or idea turns the clue into evidence. Finally, we rest in what we know now in a picture you can hold with your eyes closed. When we say measurement, I will name what was measured and what tool made it possible. You will hear that pattern again and again, and you never need to hurry. If a detail drifts past, it is fine to let it drift. I will repeat the takeaways in soft recap sentences so you always have a spine to follow. If you fall asleep, that is a success, and the thread will keep moving gently. If you wake later, listen for the next recap line and you will rejoin without effort. Sometimes I will place an open loop gently on the table and return to it later. That means I may mention a result now, then come back with the confirming observation. There will be no jump scares, no sharp turns, and no sudden changes in volume. Just steady narration, quiet transitions, and a few pauses where nothing new is asked of you. To make the listening easy, here are 3 anchors you can picture in the dark. Anchor 1 is how to listen. Keep only the recap line and let the rest float. Those recap lines are meant to land softly, even if you are half asleep. Now and then, I will slow down on purpose, letting the same idea pass twice quietly. Anchor 2 is a simple ladder of scale, moving outward in slow steps. Start with Earth, a familiar sphere under a thin sky. Then drift to the sun, a warm lamp holding the planets in place. Then to nearby stars, quiet neighbors in the dark. Then to the Milky Way, a wide river of stars we live inside. Then farther still, to the observable universe, the widest horizon light can show. Anchor 3 is the trio we return to. How far, how long ago, and what the light carries. Distance is measured with careful comparisons and repeating patterns. Time is carried by travel, so looking far is also looking back. And light is a messenger, carrying color, rhythm, and faint fingerprints of atoms. If you prefer numbers, listen for a few gentle ones that return like landmarks. They will be repeated slowly and never delivered in a fast burst. If you prefer images, follow the metaphors and let exact values fade away. Either way, the meaning stays. Evidence builds by repetition. Tonight's stories are anchored in real instruments and carefully checked timelines. Behind the scenes, each mystery has a simple fact spine, key dates, key tools, key results. That spine keeps our path straight so one section does not contradict another. You will hear quiet mentions of how discoveries were tested, not just announced. A photographic plate, a radio receiver, a space telescope, a laser interferometer, each listening in its own way. And when a result became widely accepted, it was because others could repeat it. Mostly, though, we will stay with the method, not the drama, because the soothing part of science is that it does not depend on one shot of certainty. It depends on calm checks, repeated observations, and shared results. And if a worry from today returns, set it on the phrase, one mystery at a time. So as you settle in, choose one small preference for tonight. Do you want to track the story by numbers or by pictures in the mind? Whichever you choose, I will keep the pace slow and predictable. And every so often, I will offer a short summary so your attention can unclench. With our roadmap set, we begin with the mystery that reshaped every other question. Is the universe still? Or is it quietly stretching, even as we rest? Tonight's first mystery is gentle but foundational. The universe is expanding, which sets the rhythm for everything else we will meet later. Before the word expanding became ordinary, the night sky felt like a fixed dome, with stars pinned to a quiet background. Then astronomers began to notice that many faint, fuzzy galaxies carried a subtle signature, as if their light arrived slightly stretched. That stretched light is called redshift, because the waves shift toward the red, meaning each wave arrives longer than when it left. Imagine a calm bell tone that slowly lowers as it travels, not because it weakens, but because the space in between has changed. Redshift is not a feeling or a guess. It is a measurement made by splitting light into a spectrum and reading its fine lines. Those lines are like familiar notes in a song, placed by atoms, and they tell us when light has been shifted along the way. In the early 20th century, a few careful observers saw these shifts and wrote them down, even when the meaning was unclear. One of those early measurements came from Vesto Slipher, who recorded galaxy spectra that already leaned toward red. Many galaxies looked as if they were moving away, a sky full of quiet departures recorded on photographic plates. This mattered because if galaxies are receding, the universe is not timeless and still. It has a history and a changing scale. A changing scale means there is an age to estimate and a story to reconstruct using clues that have been traveling toward us. At first, there was tension between a universe that stays the same and a universe that changes, and the data spoke softly. Some people preferred a static picture because it felt stable and complete, and because the mathematics was familiar. Albert Einstein even added a term to his equations to allow a static universe, before later evidence made change unavoidable. Others noticed that the observations did not sit easily inside a perfectly still cosmos, no matter how patiently you adjusted it. To understand what happened next, we need two kinds of measurement: how fast something seems to recede and how far away it is. Speed, in astronomy, can be inferred from redshift by comparing where spectral lines should be to where they appear. Distance is harder because there is no cosmic ruler you can hold up to the sky from your bedroom window. The first rung of the ladder uses parallax, the tiny shift of a nearby star as Earth moves around the sun. Instead, astronomers built a distance ladder step by step, using objects whose brightness or behavior can be trusted. Each rung depends on the one below it, so the quiet challenge is calibration, making sure the ladder does not wobble. A key rung is a kind of star called a Cepheid variable, which brightens and dims with a steady, repeatable rhythm. Henrietta Leavitt discovered that the period of that rhythm is linked to the star's true brightness, a calm law hidden in data. Leavitt found her pattern while studying Cepheids in the Small Magellanic Cloud, where distance differences were less confusing. If you know a Cepheid's true brightness, and you measure how bright it looks from Earth, you can infer its distance. It is like recognizing a familiar lamp across a dark room. If it looks dimmer, you know it must be farther away. This method is gentle but demanding, because dust can dim light, and instruments can add small biases without meaning to. So astronomers learned to correct for dust, to compare colors, and to use many Cepheids rather than trusting a single one. In 1929, Edwin Hubble combined distances to galaxies with measured redshifts and saw a simple pattern emerge. On average, the farther a galaxy appeared, the larger its redshift tended to be, like a slow slope that kept its shape. This was not a perfect line, because galaxies also have local motions, like leaves drifting on a river as the river itself flows. But the overall trend was hard to ignore. Distance and redshift were linked across the sky. The universe was not only full of galaxies, it was full of a relationship between where they are and how their light arrives. When you interpret that relationship, the simplest picture is expansion. The fabric of space increases the distances between galaxies. Later work revised the exact steepness of that slope, but the existence of the slope itself remained steady and repeatable. Notice the quiet wording. Galaxies are not necessarily racing through space like cars on a road. Instead, the space between them changes, so even galaxies that are calmly coasting end up farther apart over time. To keep this from feeling abstract, picture dots on the surface of a slowly inflating balloon. Each dot sees every other dot drifting away, and the farther dots seem to separate faster without any special center on the surface. The balloon is only an analogy, so we keep the focus on distances changing, not on an edge or a place the balloon expands into. When we ask, expanding into what? We are often importing room-like thinking into a story that is about the room itself changing. In modern cosmology, expansion is a change in the scale of space described by a scale factor that grows with time. You do not need the equation tonight. You only need the calm idea that space can stretch the paths that light travels. And if space stretches, light waves can stretch too, arriving longer and redder than they began. That is why redshift becomes a natural tracer of cosmic history, a quiet record written into photons. Still, early distance estimates were uncertain because the ladder was short and the calibration was not yet precise. If your ladder is slightly off, your inferred speeds and ages can be slightly off as well, and the universe's timeline shifts. Over decades, astronomers improved the ladder by measuring stellar parallax more accurately and by observing sephides in more galaxies. Space observatories helped by seeing sephides through less atmospheric blur and by extending observations into steadier wavelengths. Then came brighter beacons. Type 1, a supernova, which can outshine whole galaxies for a time and be seen very far away. They are not identical by nature, so astronomers learned to standardize them by their light curve shapes and colors. That standardization is careful work done with large samples because one unusual event can mislead if you lean on it too hard. Dust can also redden and dim supernova light, so modern analyses model dust and compare different host galaxies. Selection effects matter too, because distant surveys tend to notice the brightest objects first, which can tilt a conclusion. So the calm rule is repetition and cross-checking, using many events and independent methods to see if the same story returns. When those type 1 supernova distances are compared with their redshifts, the expansion pattern appears again, farther out. In the late 1990s, supernova surveys pushed the ladder farther, showing expansion over long stretches of time with new precision. And something else becomes visible later. The expansion rate has not been perfectly constant across cosmic time. We will meet that change when we reach dark energy, but for now we stay with the first discovery. Expansion itself is real. Modern cosmology also tests expansion using the cosmic microwave background, a faint glow that maps the early universe's conditions. That glow carries a pattern of tiny temperature variations, and those patterns depend on how the universe expanded afterward. Another check comes from large-scale structure, the way galaxies cluster into filaments and wide, gentle voids. In that clustering, there is a subtle preferred scale, a leftover ripple from early sound waves in hot matter and light. That scale is traced through baryon acoustic oscillations, which act like a cosmic ruler laid across the universe. It is a ruler you do not hold in your hand. It is a statistical imprint measured by counting galaxies across huge volumes. Wide galaxy surveys map these patterns by measuring millions of galaxies, turning the sky into a calm, three-dimensional chart. Yet it agrees again and again with the broader expansion story drawn from redshifts, sephides, and supernovae. You can picture baryon acoustic oscillations as a faint ripple, a frozen ring from early sound stretched wide by expansion. When independent methods agree, the feeling is not excitement, but relief, like hearing the same quiet answer in several rooms. Now, let's clear a common confusion without hurry. Does expansion stretch everything we touch? It does not stretch bound systems that hold themselves together strongly, like your body, your bed, or even the solar system. On small scales, gravity and other forces dominate, keeping distances steady, while expansion is noticeable only across vast emptiness. So you do not wake up longer in the morning because the universe expanded overnight. Expansion shows up when you compare galaxies separated by millions of light years where space is thin and mostly quiet. That is why the evidence lives in careful surveys and spectra, not in everyday objects in a bedroom. A helpful image is a gentle rubber sheet. Close points can stay pinned, while far separated points slowly drift apart. Another confusion is the idea of a center, as if the universe began at one point in a larger container. In the simplest models, every region sees other regions receding, and there is no special central place to point to. Again, the balloon surface helps. No dot is the center of the surface, even though all distances on the surface grow. If your mind wants one calm sentence to hold, it is this: expansion is a pattern linking light's stretch to distance. Light gives us the redshift, distance gives us the ladder, and together they tell a consistent story of a changing scale. This story also hints at a deeper consequence. If we run the expansion backward, things were closer, hotter, and denser. And if that is true, there should be a leftover glow from that earlier time, cooled and softened by the same stretching. For decades, that glow was a prediction waiting patiently in theory and in instrument noise. Then, by accident and careful checking, it was found as a steady radio hiss that would not go away. We will listen for that hush next and see how it turned a cosmic argument into a quiet measurement. Before we move on, notice the gentle question to keep in mind. If light can stretch, what else can it carry from the past? Could it carry a record of temperature, a faint pattern, or the fingerprints of the earliest matter? You do not need to answer it. You only need to let it sit like a pebble in your pocket as the story continues. Now, take a slow breath and return to the recap line, the one that will guide you forward. Expansion is not a guess. It is a measured relationship between distance and the stretching of light. And now we turn to the leftover glow, so even and gentle it almost sounds like nothing at all. If this slow pace feels right tonight, tap save. So this story is one touch away on harder evenings. No other choices, just that small step, and we can keep drifting together through calm evidence. Now we listen for the universe's quiet afterglow, a gentle background light that fills every direction. It is called the cosmic microwave background because today it arrives as long, cool waves, not because it is small. Before anyone detected it, some physicists predicted it as a simple consequence of a hot, dense beginning. If the early universe was once like a warm fog of light and matter, that warmth should not vanish completely. It should cool as space expands, fading into a soft, even glow that still surrounds us. So the prediction was not a dramatic fireball memory, but a calm, measurable background everywhere in the sky. What would count as proof was also clear. It should be nearly uniform, coming from all directions at once, and it should have a thermal spectrum like the light from a warm object, only cooled to a very low temperature. A thermal spectrum is a special shape, smooth and rounded, that tells you the light once shared a common temperature. In other words, it is the signature of something that was once well mixed, like soup that had time to settle. At first, this was only a prediction, and predictions are easy to say and hard to test. Radio technology had to mature, and instruments had to become quiet enough to hear a whisper behind everything else. Then came the part of the story that feels almost tender. The discovery arrived as a nuisance. Two radio engineers, Arno Penzias and Robert Wilson, were working with a sensitive horn antenna. They were not searching for the universe's beginning. They were trying to make their receiver behave. Again and again, they found the same thing. A steady extra noise, a constant hiss they could not erase. It was there at night and in the day, in winter and summer, and in every direction they pointed. They checked the electronics, they checked the amplifier, and they measured the antenna again with patient care. They even investigated local sources, including a layer of pigeon droppings inside the equipment, and cleaned it out. But the excess noise remained calm and stubborn, like a soft blanket of sound over the sky. At nearly the same time, another group was thinking about that old prediction with fresh seriousness. At Princeton, a team led by Robert Dickey was preparing to search for the expected background. When word of the unexplained hiss reached them, the pieces aligned with quiet clarity. The unwanted noise matched the predicted leftover radiation from a hot early universe, cooled by expansion. This is one of the most soothing moments in science, and annoyance becomes a measurement when two stories meet. Notice what strengthened the case. It was not one lucky glance, but the careful removal of other explanations. If it were from the ground, it would change with direction. If it were from the instrument, it would change with setup. But it stayed even, steady, and all sky, which is exactly what the prediction required. So the cosmic microwave background entered science as a simple fact. There is a faint, uniform glow everywhere. You can picture it as the universe's oldest light still traveling, stretched into microwaves by the expanding space. Microwave here means a long wavelength, longer than visible light, because the waves have been stretched over time. Expansion does not only separate galaxies, it also lengthens the waves that cross that growing distance. So a once hot glow becomes a cool glow, and a once bright color becomes something our eyes cannot see. Now let's pause with a quiet imagination prompt. Picture a warm ember cooling for billions of years. As it cools, it shifts from bright to dim, then to red, and then into darkness, still warm in a way we cannot see. The cosmic microwave background is like that ember, not in one place, but spread through all of space. Still, the discovery is only a beginning. What mattered next was the spectrum, the precise shape of the glow. If you want one calm reason, it is this: stories can be debated, but spectra can be measured and compared. A thermal. Blackbody spectrum is hard to fake with ordinary scattered light and local radio sources. It is a fingerprint of equilibrium, a once shared temperature, and a deep simplicity in nature. So scientists built instruments designed not just to hear the hiss, but to map its shape across frequencies. In the late 1980s and early 1990s, a satellite called the Cosmic Background Explorer was launched. One instrument on it, called the Far Infrared Absolute Spectrophotometer, measured the spectrum with extraordinary care. The result showed the cosmic microwave background matches a near-perfect blackbody curve. I will say the number softly. The temperature is about 2.7 degrees above absolute zero. That is not the temperature of your room. It is a measure of the radiation field that fills space itself. It is comforting in a way, because it is stable, universal, and the same for every listener in every galaxy. When people say the temperature of space, they mean this background glow, not the absence of all motion and life. Space is not truly empty. It holds a quiet bath of photons, a gentle sea of ancient light. With the spectrum measured, the big question became sharper. If the glow is so uniform, how did structure form? Because galaxies and clusters exist, and they are not spread perfectly evenly like mist. The answer lives in tiny ripples, variations so small that early instruments could barely perceive them. The same satellite also carried detectors to map slight differences in the glow across the sky. Those differences are not large swings. They are minute, only a few parts in 100,000. In everyday language, they are millionths of a degree, a faint pattern on an otherwise smooth background. This is where the cosmic microwave background becomes not just evidence of a hot past, but a blueprint of a future. The ripples are the seeds that gravity can slowly grow into galaxies, like gentle dents that deepen over time. The universe began smooth, but not perfectly smooth, and that slight imperfection is a gift. It means there was a starting pattern, a soft texture that later became the grand web of galaxies. Later missions refined this map with greater sharpness and quieter noise. One was the Wilkinson Microwave Anisotropy Probe, which made the pattern clearer and measured key cosmic parameters. Another was the Planck satellite, which pushed the precision further, mapping tiny fluctuations in exquisite detail. Each mission was a calm consistency check, asking if the early universe picture matched what we see today. The patterns in the glow depend on the universe's contents, because matter and light interacted in the early plasma. They also depend on how expansion unfolded, because expansion sets how scales project onto the sky. So the cosmic microwave background links to the expansion we just discussed, like 2 pages from the same notebook. There is also a simple large feature called the dipole, a gentle warm and cool direction caused by our motion. It is the feeling of moving through the photon sea, like a slight headwind in one direction and a tailwind behind. When we subtract that motion effect, the remaining ripples are the true ancient pattern we want to interpret. Those ripples tell us about ordinary matter, the matter that forms stars and planets and people. They also point to something else, because ordinary matter alone does not fit the pattern and the later structures. In the cosmic microwave background, the best fitting models include dark matter, which we will meet in a later section. Dark matter does not glow, but it adds gravity, helping tiny ripples grow into galaxies without breaking the early smoothness. So the afterglow is quiet, but it carries an enormous amount of information, like a soft-coded message. Even so, we keep the tone simple. It is a fossil glow, measured across the whole sky, with a thermal spectrum. If you like images, Imagine a thin fog of light filling space, with barely visible swirls embedded within it. If you like numbers, keep only the calm landmark, about 2.7 degrees above absolute zero. Either way, the evidence is steady, a prediction, then a discovery, then a spectrum, then maps, each reinforcing the last. This is also a story about instruments learning to listen, and about scientists learning what counts as noise. The horn antenna heard a hiss that did not belong to any single star, and that was the clue. The satellite measured the spectrum, and that turned the clue into a measurement you can trust. The maps revealed ripples, and that turned the measurement into a history of structure. Now we add a gentle link forward, because those ripples relate to a later puzzle about galaxy motion. Galaxies rotate in ways that suggest more gravity than their visible stars provide, like a wheel that keeps its speed. The Afterglow's pattern hints that an invisible form of matter helps shape that story. We will come back to that carefully when we reach dark matter, one quiet step at a time. For now, take a soft recap sentence and let it settle. The cosmic microwave background is an ancient, all-sky glow cooled by expansion and measured as a precise thermal spectrum. And it is smooth, but not perfectly, with tiny ripples that became the seeds of galaxies. Now we open a new loop because radio astronomy did not only find a hush, it also found clocks. As antennas improved, observers began to notice repeating signals, pulses that were too regular to dismiss as ordinary noise. At first, these pulses sounded almost artificial because the rhythm was so clean and steady. But the sky was teaching a new lesson. Some stars can become lighthouses, sweeping beams through space as they spin. In the next section, we move from a uniform hush across the sky to a rhythm you can almost count in the dark. Here is the quiet spine so far. Galaxies' light arrives stretched, and when that stretch is compared with distance, it shows that space itself is expanding. And across the whole sky, there is a nearly uniform microwave glow, the cooled afterglow of a hotter, denser beginning. Now we pause and add nothing new. If you are still listening, notice your breathing for 3 slow counts. Inhale gently and let your shoulders soften. Exhale slowly, as if you are fogging a window with warm air. Inhale again, calm and unforced. Exhale and let the ideas settle like dust in still light. For a few seconds, you do not need to follow anything at all, just the steady voice and the quiet dark around you. When you are ready, we will return to the sky and notice smaller signals riding on top of that background. After the sky's uniform hush, we notice something smaller riding on top of it. It is not a glow this time, but a rhythm. A repeating pulse in radio waves, steady enough to feel like a clock. If you could hear the sky, which would you prefer tonight? A continuous hush or a calm, regular ticking? The story begins with careful listening and with a lot of patience. In the 1960s, radio astronomers were recording long strips of data on paper charts. The charts looked like quiet scribbles, mostly noise, mostly ordinary sky. Then, a few marks appeared that did not behave like noise. They repeated with the same spacing again and again. At first, it was easy to doubt them. A repeating signal can come from equipment, or from human activity, or from the atmosphere. So the first response was not belief, but checking. The observers changed settings, changed cables, and pointed the antenna in different directions. They watched the signal move with the stars, keeping time with Earth's rotation. That was an important clue because it suggested the source was truly celestial. Even then, skepticism stayed. Nature is full of patterns, but it rarely clicks like a metronome without a reason. The pulses were so regular that people joked gently about intelligence. But jokes are not conclusions, and the team treated the idea like a placeholder, not an answer. They recorded more data. They compared nights. They checked whether the pulses arrived a little earlier each day, as a star would. The pattern held steady in the way the sky itself is steady. It was not a local broadcast drifting in and out. It was something out among the stars, repeating with quiet persistence. When the evidence was strong enough, the discovery was announced. A new class of object entered astronomy, first described only by what it did. A source that pulsed, like a lighthouse, but with astonishing regularity. The name pulsar came from pulsing star. The first mystery was simple to say and hard to explain. What in nature could pulse so quickly, so steadily, for so long? To answer that, astronomers reached for a deeper idea: stellar remnants. A star does not live forever in one form. When a massive star runs out of fuel, gravity wins the long contest. The outer layers can be thrown outward in a supernova explosion, and the core can collapse into something far denser than an ordinary star. This is where we meet the neutron star, gently and without hurry. A neutron star is what remains when gravity squeezes matter beyond normal atoms. Electrons and protons are pressed together, leaving a sea of neutrons. The result is a sphere only about the size of a city, but with the mass of a star. It is one of the most extreme objects we can still describe with measured physics. Now we return to the pulses and ask how such an object could make them. The key is rotation. If a normal star spins and then shrinks dramatically, it spins faster, like a skater pulling in their arms. A neutron star is small, so it can rotate very rapidly without flying apart. The second key is magnetism. Neutron stars can have magnetic fields far stronger than anything we create on Earth. Those magnetic fields guide charged particles near the star, and those particles can produce beams of radio emission along the magnetic poles. Now, picture the lighthouse model in a calm way. The star spins steadily. The beams sweep through space. If one beam crosses Earth, we see a pulse each time it passes our line of sight. The star is not turning on and off. We are simply moving in and out of the beam, like watching a slow rotating lantern. This model makes the regularity feel natural rather than eerie. A spinning object can keep time, and in space with little friction, it can keep time very well. But scientists did not accept the idea only because it sounded elegant. They tested it against what was observed. If pulsars were rotating neutron stars, the pulse period should be stable but not perfectly frozen. The rotation should slow gradually as energy is lost. That slowing should be measurable as a gentle drift in arrival times. And indeed, careful timing showed that many pulsars slowly spin down. The sky's clocks were not magical. They were physical, and they were spending energy in a measurable way. That measurement mattered because it moved the story from metaphor to mechanism. It also helped rule out simpler ideas, like a star that physically expands and contracts each second. A whole star cannot puff in and out that fast without tearing itself apart. Rotation, on the other hand, is a quiet and durable explanation. So pulsars became rotating neutron stars, not by a single argument, but by a chain of matching clues. Now we add a second kind of evidence: association. If neutron stars are born in supernovae, some pulsars should sit inside supernova remnants. Astronomers looked for pulses coming from famous remnants. One of the most important was the Crab Nebula, the remnant of a supernova seen in the year 1054. Inside that nebula, a pulsar was found, pulsing rapidly and reliably. The match was powerful. A known supernova remnant and a clock-like source at its heart fit the birth story of neutron stars. The Crab pulsar also pulses in more than radio. It can be seen in optical light too, like a faint strobe that confirms the timing across wavelengths. That multi-band agreement made the identification feel solid and shared. Another remarkable case was the Vela pulsar, tied to another supernova remnant. Each association strengthened the idea that pulsars are endpoints of stellar lives. Now let's hold the concept of timing, because timing is where pulsars become tools. A pulsar's pulses arrive with such consistency that you can predict them far into the future. When they arrive early or late, it often means something in between has changed. It could be the pulsar's own rotation slowing. It could be motion through space. Or it could be gravity affecting the path and the flow of time. This turns pulsars into natural laboratories for physics. One famous example involves a pulsar in a binary system, orbiting another compact object. By timing the pulses over years, astronomers can measure the orbit with exquisite precision. They can see tiny changes, like a slow shrinking of the orbit as energy is carried away. This is where pulsars help test ideas about gravitational radiation long before direct detectors existed. Even if you do not keep the details, keep the feeling. A steady pulse can reveal subtle shifts that a less regular source would hide. Another quiet detail is something called a glitch. Sometimes a pulsar suddenly spins a little faster, as if its interior rearranged. These glitches are rare and small, but they remind us the star is a physical object, not a perfect clockwork toy. They also hint at an exotic interior, where super-dense matter may behave in unfamiliar ways. So pulsars are both steady and alive, stable over years, yet capable of tiny surprises. Now we step into modern use, softly. Astronomers have found many kinds of pulsars, including millisecond pulsars that spin hundreds of times each second. These tend to be old neutron stars that were spun up again by a companion star. Matter can flow from the companion, adding angular momentum like a gentle push over a long time. This process is sometimes called recycling because it gives the pulsar a second, faster life. Millisecond pulsars can be especially stable, making them excellent long-term clocks. When you gather many such clocks across the galaxy, something beautiful becomes possible. You can treat the sky itself as a timing instrument. This idea is called a pulsar timing array. It is not one device in one place. It is a network of distant pulsars, each one keeping its own rhythm. If a very long wavelength gravitational wave passes between us and them, it can slightly stretch and squeeze the distances. That stretch changes pulsar arrival times in a correlated way across the network. The effect is tiny, and it takes years of calm observation to seek it. But the method is gentle, like listening for a slow swell in an ocean by watching many buoys. Soon, much later in this video, we will meet another way of sensing space-time. That one uses lasers on Earth, comparing lengths with astonishing precision. For now, it is enough to know that pulsars help teach us to listen to time itself. Let's also return to the human side for a moment, because it matters for how science avoids mistakes. The discovery required careful recording, and it also required doubt. The team did not stop at the first strange chart. They kept testing whether the signal belonged to the sky or to their own setup. They looked for repeatability, because repeatability is how noise turns into knowledge. This is the calm heartbeat of the scientific method, especially in a field where you cannot touch the source. Now we take a gentle recap sentence, the kind you can carry even as you drift. Pulsars are rotating neutron stars, identified by repeatable timing and by their astrophysical context. They pulse like lighthouses because beams sweep past us as the star spins. Their slow spin down is measured, not imagined, and it reveals real energy loss. And their stability makes them tools, clocks that can test gravity across the galaxy. Now we place one last open loop on the table, quietly. A neutron star is one outcome of stellar collapse, dense, but still a physical surface. So what is the other ending when collapse goes farther, past the point where light can easily escape? In the next section, we step from the ticking remnant to a darker center. We will follow light as it bends, and matter as it flows inward toward what we call a black hole. If you are in bed, set your phone face down and let the audio do the work. Keep the volume low, keep the pattern simple, and rest your eyes while the story continues. Now we move from a ticking remnant to a darker outcome of collapse. This mystery begins in equations long before anyone had a telescope that could confirm it. In the early days of general relativity, the math allowed an extreme possibility. Gravity so deep that escape becomes impossible. At first, it sounded like a strange corner case, a curiosity with no clear home in the real sky. But science is patient, and the sky eventually provided the clues. So tonight we'll follow the same calm pattern: question, clue, breakthrough, and what we know now. The question is simple to say. Can matter collapse into a region so compact that even light cannot leave once it crosses a boundary? That boundary is called the event horizon. It is not a solid surface you could touch. It is a threshold in space-time, where the paths that light can take no longer point outward. A black hole is not a hole in the usual sense. It is a region defined by gravity and geometry. not by emptiness. And it is not a place that sucks everything like a hungry drain, far away. Its gravity behaves like the gravity of any object with the same mass. If the sun were replaced by a black hole of the same mass, Earth would still orbit in nearly the same way. The difference appears only close to the horizon, where space-time curves sharply and paths bend strongly. So what would count as evidence? We would need to infer a lot of mass packed into a very small region. And we would need to see its gravitational influence clearly, through motion, light, or both. At first, black holes were invisible by definition, so the early evidence had to be indirect. The sky offered a gentle clue in the form of binary systems. A binary system is two objects bound together, orbiting a shared center of mass. Sometimes one of those objects shines brightly, while the other is dark or faint. If the bright one wobbles in a regular way, we can infer the mass of the unseen companion. This is like watching a lantern on a string circle an empty point and realizing something heavy must be there. Astronomers measure that wobble through changes in the star's spectral lines. Those lines shift back and forth as the star moves toward us and away from us. From that motion, they can estimate orbital speed, orbital period, and the companion's minimum mass. This is where the evidence becomes quietly persuasive. If the unseen companion's mass is too large to be a neutron star, then another explanation is needed. Neutron stars have limits set by physics, because matter cannot be packed endlessly without changing form. So when the inferred mass crosses those limits, the dark companion becomes a strong black hole candidate. One famous early system was called Cygnus X1. It appeared as a bright source of X-ray emission in the direction of the constellation Cygnus. The X-rays were a clue that something was heating matter to extreme temperatures. But a black hole has no glowing surface, so where would the light come from? The answer is accretion. Accretion is the slow gathering of matter, as gas spirals inward under gravity. As the gas falls, it does not drop straight down like a stone. It forms a swirling disk because it carries angular momentum, like water circling a quiet drain. Friction and turbulence in that disk convert orbital energy into heat. Near a compact object, that heat can become intense. Hot enough to shine in X-rays, which are high-energy photons our eyes cannot see. So a black hole can be revealed by the light of what falls toward it, not by a surface, but by the glow of infalling matter. This is a key idea for tonight. Black holes are often seen through their influence on light, not light from themselves. In X-ray binaries, the disk can brighten and dim as the flow of matter changes. Sometimes jets appear too, narrow streams that carry energy outward along magnetic fields. Those jets can extend far beyond the binary system, like a quiet line drawn into space. Even so, astronomers stayed cautious. A bright disk does not automatically mean a black hole, because neutron stars can also accrete and shine. So the cleanest step is the mass estimate. Measure the orbit carefully, account for the tilt of the system, and see whether a neutron star remains possible. In several cases, the numbers made the neutron star option very hard to keep, and that moved black holes from speculation to a category of objects with strong observational support. Now let's widen the view, from stellar mass black holes to supermassive ones. If stellar black holes are born from dying stars, supermassive black holes live at the centers of galaxies. Their masses are so large that they shape the motion of stars and gas on enormous scales. At first, this too was an inference, a pattern in motion rather than a visible object. We infer wind by watching leaves, and we infer a central mass by watching orbits. Orbits are persuasive because they tie together distance, time, and geometry. If you can track a star's position over years, you can reconstruct its path. And from that path, you can calculate how much mass must sit inside it. This method is gentle because it uses repeated measurements rather than a single dramatic moment. In our own Milky Way, the galactic center is hidden behind dust in visible light. So astronomers used infrared observations which pass through dust more easily. Over many years, they tracked individual stars near the center. Those stars move fast, and they trace tight arcs around an unseen point. One star in particular became a famous marker because its orbit is well measured and repeats. Its path implies a mass of about 4 million suns concentrated in a region smaller than our solar system. That is the quiet punchline. Enormous mass, extremely compact. A cluster of ordinary stars packed that tightly would likely collide, shine, and spread out. But the central mass remains dark, steady, and confined. The simplest explanation is a supermassive black hole. We call this central object Sagittarius A star. It is not a normal star. It is the name for the compact source at the Milky Way's center. Its presence is felt through the motion of nearby stars, like a heavy stone under a thin sheet. Again, this is evidence through influence. A black hole announces itself by shaping the paths around it. Now take a soft check-in thought. Were you surprised that the strongest evidence can come from patient orbit tracing rather than a direct photograph? Just notice your answer and let it pass. For a long time, black holes remained convincing but still indirect. We had strong inferences, strong models, and repeatable patterns, but not an image-like measurement of the horizon's effect. Then came a worldwide instrument built from a simple idea. If you link radio telescopes across Earth, you can create a virtual telescope nearly the size of Earth. This technique is called Very Long Baseline Interferometry. Instead of one mirror, you use many dishes separated by oceans, synchronized by precise timing. Each telescope records the incoming radio waves, along with exact timestamps. Later, the recordings are combined, and the sky image is reconstructed from the interference patterns. The project that did this for black holes is called the Event Horizon Telescope. To keep it easy for speech, I will say the full name each time. The Event Horizon Telescope observed at millimeter wavelengths, where the view can cut through some of the surrounding haze. It also observed from high, dry sites, because Earth's atmosphere can absorb these signals. When the Event Horizon Telescope turns its many dishes into one instrument, it is still not a simple camera. It measures fragments of information, and the final image is carefully reconstructed. That reconstruction is tested many ways to ensure it is not an artifact of the method. The first widely shared result was an image-like ring around the black hole in the galaxy Messier 87. That galaxy sits far away, yet its central black hole is enormous, making its horizon appear large enough to resolve. What the Event Horizon Telescope revealed was a bright ring with a darker center. The bright ring is not the horizon itself. It is light from hot plasma swirling around the black hole, bent by gravity into a near circle. The dark center is called the shadow. It is the region where many paths of light are captured or redirected away from us, leaving a dim hole in the view. In a calm way, it is a silhouette made by curved spacetime. This was a turning point. A feature predicted by relativity was measured in shape and scale, not only inferred from motion or brightness changes. The ring's size matched expectations based on the black hole's mass and distance, and the overall appearance matched models of light bending in strong gravity. Later, the Event Horizon Telescope also produced an image-like result for Sagittarius A star at our own galactic center. This was harder because Sagittarius A star varies on shorter time scales, like a restless glow around a steady darkness. So the team needed careful methods to account for that variability while reconstructing the view. The results still showed a ring-like structure consistent with a shadow, a measured feature rather than a story. It is worth saying gently what this image is and is not. It is not a portrait of a black surface. It is a map of radio brightness shaped by gravity near the horizon, and it is built from data gathered across Earth, combined with well-tested algorithms. So the evidence is both physical and mathematical, fitting the theme of this mystery. Math suggested the possibility. Light and motion provided indirect support, and now radio measurements have given us shadow-like images that match the predicted geometry. Black holes also helped solve other puzzles in astronomy. Quasars, for example, are extremely bright sources seen in the distant universe. For a time, their energy output seemed hard to explain with ordinary stars alone. Accretion onto supermassive black holes provides a natural engine. Matter falling inward can release a large fraction of its energy as radiation, far more efficiently than burning fuel in stars. Jets from galactic centers also fit into this picture. They can be powered by accretion disks and magnetic fields threading the region near the black hole. So black holes became a quiet, unifying idea, linking compact X-ray sources, galactic centers, and distant beacons. They also became a way to test general relativity where gravity is strong. Most tests of relativity happen in gentle fields, like the solar system. Near a black hole, the field is much stronger and light bending becomes dramatic but still measurable. By comparing observations to predictions, scientists can check whether relativity continues to hold in these extremes. So far, the results have been remarkably consistent with Einstein's theory. But we keep the tone calm. The work continues, and measurements keep improving. Now we place a soft bridge toward a later mystery. Black holes do not only sit quietly. They can merge, and when they do, they can release energy in a new form. Not as light, but as ripples in space-time itself. We will meet that story when we reach gravitational waves. For now, just keep the gentle idea that black holes can collide and the universe can respond with a faint tremor. Before we move on, let's clear one more common image that can mislead. A black hole is not a roaming mouth that eats everything nearby. If you keep your distance, its gravity is ordinary for its mass. What makes it special is compactness. The same mass pressed into a smaller region makes gravity stronger close in, changing how light and matter behave. That is why astronomers look for compact mass. A lot of mass in a very small volume. And that is why orbits and shadows are so important. They speak directly about compactness. Now we take our recap sentence, slow and simple. Black holes are inferred by compact mass and the light of infalling matter, and now even by shadow images. They began as mathematics, became likely through binaries and orbits, and became measurable through the Event Horizon Telescope. And now we open the next loop because invisibility comes in more than one form. Black holes are invisible because they are compact and extreme. But some invisible influence is not compact at all. Some missing mass seems spread through and around galaxies, shaping their rotation and their structure. When astronomers measure how fast galaxies spin, they find a gentle mismatch between visible matter and needed gravity. That mismatch points to something widespread, not a single dark center. So from one kind of invisible, compact and intense, we will move to another kind, gentle and everywhere in the math. Next, we follow the missing mass problem and see why galaxies behave as if held by an unseen scaffold. Let's do a gentle scale reset, then return to the story. A stellar black hole is small by cosmic standards, usually a few tens of sun masses. A supermassive black hole is huge, often millions to billions of sun masses sitting quietly in a galaxy center. And dark matter is vast, not a single object, but a wide halo that extends beyond the visible disk of a galaxy. If numbers feel sharp tonight, let them blur. Keep only 3 soft words: small, huge, vast. Choose one word for a breath, then release it. Small for a collapsed star. Huge for a galactic center. Vast for the unseen halo that holds a galaxy's motions. With that scale in mind, the next mystery will feel more natural, because galaxies move as if there is more there than we can see. Now we arrive at an invisible influence that is not compact like a black hole, but wide and quietly present across galaxies. This is called dark matter, and the mystery is solved in one clear sense. The measurements demand extra gravity beyond what we can see. What remains open is the deeper question of what dark matter is made of. So tonight we separate 2 ideas gently. First, the existence. Something unseen adds mass and shapes motion. Second, the nature. The exact particles or substance are still being searched for. The clue that first bothers the mind is not a photograph. It is motion, calm and repeatable, written into the way stars and gas orbit. Imagine a spiral galaxy as a slow, rotating disk of starlight. If most of the mass were in the bright center, you would expect outer stars to orbit more slowly. That expectation comes from the same kind of reasoning you use in a solar system. Farther out means weaker gravity from the center, so a slower orbit should be enough. But when astronomers measured real galaxies, the outer parts did not slow down the way the simple picture predicted. Instead, the orbital speed stayed high, even far from the bright center. This is what people mean by a flat rotation curve. Flat here does not mean motionless. It means the speed stays roughly steady as you move outward instead of declining. If you prefer an image, picture a vinyl record that keeps the same gentle pace from inner groove to outer groove. If you prefer the idea, hold this sentence. The outskirts move too fast for the visible matter alone. A galaxy, in this sense, behaves as if it is wrapped in additional mass we cannot see. This extra mass is not a small hidden object at the center. It must be spread out in a broad halo, extending beyond the visible disk. Now you might wonder if the measurements were wrong or if the light is hiding ordinary matter. That is a fair and quiet question, and it was asked for decades. Astronomers checked for dim stars, cold gas, and dust that could hide mass without shining much. Some ordinary matter is indeed hard to see. But the missing amount is too large, and it shows up in too many independent ways. So the story becomes a pattern, not a single anomaly. Let's begin with the early hints on the largest scales in clusters of galaxies. A galaxy cluster is a collection of many galaxies bound together by gravity. The galaxies move within the cluster, and their speeds can be measured. If you know how fast they move, you can estimate how much mass must be holding the cluster together. Early studies found that clusters seem to need far more mass than their starlight accounted for. Fritz Zwicky is often linked to these first strong hints because he treated the cluster as a system and asked what mass it required. The language at the time was missing mass because something seemed absent from the inventory. At first, a single surprising cluster could be dismissed as a special case, but as more clusters were studied, the same need appeared again and again. That repetition is what turns discomfort into evidence. Many clusters behave as if they contain much more mass than their light suggests. And because the measurement uses gravity and motion, it does not depend on how bright the matter is. This sets a theme for dark matter. The universe keeps telling us about mass through its effects. Now we return from clusters to individual galaxies, where the case became famously clear. In the 1970s, Vera Rubin and collaborators measured galaxy rotation with careful, consistent methods. The key strength was not one dramatic observation. It was galaxy after galaxy, measured in comparable ways, showing the same basic pattern. When many different spiral galaxies share a similar kind of rotation curve, the explanation cannot be a rare coincidence. The calm inference is that an unseen halo is common, not exceptional. Rubin's work helped shift dark matter from a troubling idea into a standard part of galaxy dynamics. The conclusion was not shouted. It was repeated until it became hard to ignore. Now pause for a soft retention question, just to hold attention without effort. Which feels more convincing to you tonight? Objects moving too fast or light bending in ways that reveal invisible mass? Keep your answer private and let it float. Because the next clue is not about motion, but about light itself. This clue comes from general relativity, the same framework that guided our black hole story. Gravity curves space-time, and curved space-time bends the path of light. So a massive object can act like a lens, distorting and magnifying background light. Sometimes the effect is strong, creating arcs, rings, or multiple images of the same distant galaxy. But more often, the effect is subtle, a gentle stretching that you only see statistically across many sources. This is called weak gravitational lensing. Weak lensing does not rely on the light from the mass doing the lensing. It relies on the shape changes of background galaxies measured carefully across wide surveys. If you average over enough galaxies, you can map where extra mass must be. This produces a kind of shadow map of matter, including matter that is otherwise dark. It is a second path to the same conclusion. There is more mass than light reveals. And because it is a different method, it works as a consistency check. Now we come to a particularly clear style of argument, often illustrated by a system called the bullet cluster. The bullet cluster is a collision between two galaxy clusters. In such a collision, different components behave differently. The galaxies themselves are mostly empty space, so they pass through each other with relatively little direct collision. The hot gas between galaxies does collide and slows down, heating and glowing in X-rays. So after the collision, the gas can lag behind the galaxies. Now here is the quiet key point. When astronomers map the mass using gravitational lensing, the mass peaks align more with the galaxies than with the slowed gas. That suggests the dominant gravitating material is not simply the hot gas, which is ordinary matter. It behaves as if most of the mass is in something that does not collide much, passing through more easily. This is why the bullet cluster style evidence is often described as strong support for dark matter. It separates light, hot gas, and gravitational mass in a way that is hard to explain with ordinary matter alone. Still, we keep our tone careful. One system is persuasive, but the deeper comfort comes from many lines of evidence pointing the same direction. Now let's connect dark matter to the earlier mysteries without repeating them too much. The cosmic microwave background carries a pattern of tiny ripples from the early universe. Those ripples fit best when the universe contains a large amount of matter that does not interact with light the way ordinary atoms do. Galaxy clustering across the sky also fits better with this unseen component. In these models, dark matter helps structure form efficiently, turning small early ripples into the cosmic web. So the early universe and the modern universe tell a consistent story. Motion inside galaxies, motion inside clusters, bending of light, and ancient background patterns all agree on the need for extra mass. That agreement is soothing. It means we are not building on one fragile measurement. We are hearing the same message through different instruments and different centuries of observation. Now we gently address a common misunderstanding. Dark matter is not the same thing as a black hole population hiding everywhere. Black holes are compact, and many would produce other signatures, like strong lensing events or energetic accretion in some cases. Dark matter, by contrast, behaves as a widespread halo smooth on large scales, shaping gravity gently and continuously. Another misunderstanding is to imagine dark matter as a kind of darkness mixed with air. It is not darkness itself. It is matter that does not emit or absorb much light, at least not in ways we have detected yet. So we learn about it by gravity, which does not require light. Now we come to what remains open, and we treat it as calm uncertainty, not drama. Scientists are searching for what dark matter is made of, using several approaches. Some experiments look for rare interactions between dark matter and ordinary atoms in very quiet detectors. Some searches look for signals from dark matter annihilations or decays in space if those processes occur. Other work explores whether dark matter could be a new particle beyond the standard model of particle physics, and some ideas examine whether gravity itself might behave differently on galactic scales. But the dominant view, supported by multiple datasets, is that an unseen matter component exists in addition to ordinary atoms. So the solved part is the need, the gravitational requirement. The unsolved part is the identity, the true nature of the unseen component. You do not need to remember the candidate names tonight. Just keep the gentle distinction. Existence is well supported. Nature is still being pinned down. Now, let's make the rotation curve idea feel even more intuitive, without leaning on equations. If you stood far from a campfire, the warmth would fade with distance. If a galaxy's gravity came only from its bright center, the pull should fade too. But the outer stars do not behave as if the pull fades that quickly. They behave as if there is extra mass farther out, adding to the gravity they feel. So the halo acts like an extended scaffold, holding the rotating disk in a stable pattern. This scaffold is not rigid, and it is not a shell you could touch. It is a distribution of mass inferred from how everything moves. Now we tie this back to the quiet method you have heard all night. Question, clue, breakthrough, and what we know now. The question was why galaxies and clusters move as they do. The clue was speeds that stayed high and clusters that stayed bound despite too little visible mass. The breakthrough was treating the evidence as a pattern across many systems, then adding lensing as an independent measurement of mass. And what we know now is a consistent need for an unseen matter component, spread broadly around galaxies and across cosmic structure. Here is the recap sentence to carry forward. Dark matter's existence is supported by motion, by gravitational lensing, and by early universe background patterns, multiple routes to the same need. Now we place an open loop for the next mystery, because the method of indirect discovery will continue. Dark matter is inferred from effects, not direct images, and soon we will meet worlds beyond our solar system that were also found by effects. Exoplanets often reveal themselves through a tiny tug on a star or a small dimming as they pass in front. We will move from invisible mass shaping galaxies to invisible worlds revealed by how they tug and how they dim. And along the way, you will hear about a first close and giant planet that quietly rewrote what people thought solar systems had to be. For now, let the idea of the halo rest in your mind like a soft outline, not a thing you can see, but a shape you can infer. A quiet scaffold holding galaxies together while remaining dark to our eyes. If you are still comfortable, tap like once, no rush, so these calm science stories reach more sleepless minds. Then we will drift from invisible mass to hidden planets and learn how worlds appear as tiny tugs and soft dimming. Now we shift from invisible mass to invisible worlds, planets circling other stars. For a long time, exoplanets stayed hidden because stars are bright and planets are not. A planet is a small ember next to a blazing lamp, lost in the glare. So the key move was simple. Stop trying to see the planet at first. Instead, measure what the planet does to its star. Indirect detection can be calmer and stronger than a blurry picture, because effects can repeat, and repetition is how doubt softens into evidence. Tonight you will hear three main kinds of effects: wobbles, dips, and bends. A wobble is motion, a small back and forth in a star's path. A dip is dimming, a tiny, repeated reduction in starlight. A bend is lensing, when gravity briefly magnifies light from a more distant star. If you like a quiet prompt, choose one word to hold for a moment: wobble, dip, or lens. Then let it go and just listen to the pattern unfold. We start with the wobble method because it found some of the earliest confirmed exoplanets. Gravity works both ways. A planet pulls on its star and the star pulls back. So they do not orbit with the star perfectly still at the center. They orbit a shared balance point called the center of mass. From far away, that can look like the star is making a small, steady dance. The dance is subtle, but light carries a clue. When the star moves toward us, its spectral lines shift slightly one way. When it moves away, the lines shift slightly the other way. This is the Doppler effect, measured in light rather than sound. Astronomers use very stable spectrographs to detect these tiny shifts. They are looking for a pattern that repeats with a fixed period. A period means an orbit, and an orbit suggests a companion. The surprise was not only that planets existed. The surprise was what kinds of planets were easiest to find first. The first big wave of detections favored large planets close to their stars. These are often called hot Jupiters because they resemble Jupiter in mass but orbit much closer. They were easier because a massive close planet makes a larger wobble. The star's motion becomes stronger and quicker, so the signal stands out. In 1995, Michel Mayor and Didier Queloz announced a planet around the star 51 Pegasi. That planet, 51 Pegasi b, was a hot Jupiter, and it changed expectations overnight. Before then, many people expected solar systems to look like our own. Big planets far out, smaller planets in, and quiet, wide orbits. Hot Jupiters forced a rewrite. They suggested that planets can migrate, moving inward after formation, or that formation itself might be more flexible than the tidy early models. The calm lesson is that discovery methods shape what we notice first. We found the loudest signals before the quiet ones. Radial velocity, the wobble method, measures a minimum planet mass, because we usually do not know the exact tilt of the orbit from our viewpoint. If the orbit is edge-on, we see the full wobble. If it is tilted, we see only part of it. So astronomers speak carefully and combine methods when possible. They also watch for false positives. Star spots and stellar activity can mimic small spectral shifts if you are not cautious. So modern surveys use long baselines, multiple lines, and statistical checks. They also compare signals across different wavelengths and instruments. The goal is the same as earlier mysteries: remove local explanations until the pattern remains. As the instruments improved, radial velocity detections expanded to smaller planets and longer orbits. But there was another method that feels even more lullaby-like, because it is a simple repeated dip. This is the transit method. A transit happens when a planet passes in front of its star from our point of view. For a short time, the planet blocks a small fraction of starlight. The star dims slightly, then returns to normal. If the planet returns, the dip repeats on a schedule. That schedule is the orbital period. The dip depth tells you the planet's size compared with the star. A bigger planet blocks more light and makes a deeper dip. A smaller planet makes a shallower dip, closer to the noise. This is why steady, patient observing matters so much. From the ground, Earth's atmosphere makes star brightness shimmer a little. So space telescopes changed everything by watching without atmospheric flicker. They could stare at the same field for months, measuring tiny dips with calm consistency. One of the first famous transit confirmations came in 1999 for a planet called HD 209458b. The transit made the planet feel real in a new way because it added geometry. Now we had both a wobble and a dip for some systems. With both, you can estimate mass and size, and therefore density. Density is a quiet doorway to composition. Low density suggests a puffy gas planet. High density suggests a rocky world or an iron-rich one. Even when you do not get a perfect answer, you narrow the possibilities. A transit also gives a precise clock. The planet crosses at predictable times, and small timing shifts can reveal additional planets. This is called transit timing variations, and it is another kind of indirect discovery. Now let's picture a light curve gently. It is a line of brightness over time. Most of the line is flat and steady. Then it dips smoothly, reaches a minimum, and rises again. The shape can tell you about the orbit's tilt and the star's limb darkening. You do not need to keep that term tonight. Just remember that the dip is a measurement with a shape, not just a single point. Now we meet a mission that made transits a nightly habit for astronomy. The Kepler Space Telescope watched over 100,000 stars, searching for repeated dips. Kepler did not look for one planet. It looked for a statistical population, a census. From that census, we learned that planets are common. Small planets are especially common, even if they are harder to detect. We learned that many systems have compact arrangements with several planets in tight orbits. We learned that the universe is full of sizes we do not have in our solar system. For example, super-Earths and mini-Neptunes, worlds between Earth and Neptune in size. Some may be rocky with thick atmospheres. Some may be water-rich. Some may be something we have not imagined well yet. Another mission continued this work in a different style. The Transiting Exoplanet Survey Satellite, which you can hear as TESS, scans wide areas of sky. It focuses more on nearby bright stars. Bright stars are helpful because they allow follow-up observations from the ground and from space. So the story becomes a gentle partnership between discovery and confirmation. A survey finds a candidate, then other telescopes measure the wobble, or check for other explanations and refine the planet's properties. Because not every dip is a planet. Eclipsing binary stars can mimic a transit signal if you are not careful. Instrument noise can create repeating patterns if conditions align. So confirmation is part of the calm process. Now let's step back and appreciate the philosophy. We are finding worlds without seeing their surfaces. We are detecting their gravity, their timing, and their shadows across starlight. This is not a weakness. It is often stronger than a dim, ambiguous image, because a repeated, measured effect is hard to argue with. Still, direct images do exist in rare cases. Direct imaging is difficult because the star overwhelms the planet's light. But if a planet is young, warm, and far from its star, it can glow in infrared. With special optics called coronagraphs, telescopes can block starlight and reveal faint companions. These images are usually of wide orbit planets, not close ones. They are a reminder that different methods reveal different slices of the population. Now we add another method that feels like a quiet trick of alignment. Gravitational microlensing occurs when a foreground star passes nearly in front of a background star. The foreground star's gravity bends light and briefly magnifies the background star. If the foreground star has a planet, the planet can add a small extra bump to the magnification. This bump can be short, sometimes hours to days, so it requires constant monitoring. Microlensing is powerful because it can detect planets farther from their stars, even in distant parts of the galaxy. It does not require the planet to emit light. It uses gravity, like lensing in the dark matter story, but on a smaller scale. Microlensing events are usually one-time occurrences for a given alignment, so they can be harder to revisit. But they expand our view of what kinds of planets exist and where. Now we mention astrometry, another quiet method. Astrometry measures a star's position in the sky with extreme precision. If a planet tugs the star's position can wobble slightly over time. This is like watching a distant lantern shift side to side by a hair's breadth. Astrometry is challenging, but modern space measurements have made it far more feasible. It tends to be most sensitive to massive planets in wider orbits. So again, it complements the transit and radial velocity methods. There is also timing in a very literal sense. If a pulsar has planets, the pulses can arrive slightly early or late as the pulsar moves. This method is exquisitely precise, though it applies to rare systems. It is a gentle link back to our earlier sky clocks. So now we have a toolkit. Wobble in spectra, dip in brightness, brief lensing bumps, position shifts, and timing shifts. Each method has its own biases. Each one sees certain worlds more easily than others. Hot Jupiters were the first loud voices because they make big signals. Small Earth-sized planets are quieter and require longer, steadier watching. Planets in long orbits require time, sometimes many years, to see repeated cycles. So the catalog of known planets grows with patience as much as with technology. Now we move from detection to description, because the deeper wonder is not only that planets exist, it is that we can begin to learn what their atmospheres are like. This is done with spectroscopy, the same idea that helped measure redshifts and stellar composition. During a transit, a small fraction of starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths, so the spectrum of the star can carry faint chemical fingerprints from the planet's air. The signal is delicate, and it requires careful calibration. But when it works, it can reveal water vapor, sodium, carbon-bearing molecules, and hazes. Not always, and not for every planet, but enough to show the method is real. Another gentle way to learn about atmospheres is through thermal emission. A hot planet emits infrared light of its own. As it orbits, we see changing phases like a moon, but in heat rather than visible light. By measuring these phase curves, astronomers infer temperature distribution across the planet. They can learn whether winds carry heat from dayside to nightside. They can detect hot spots shifted from the point directly under the star. These are soft, indirect inferences, but they are grounded in repeated measurements. Some planets show evidence of escaping atmospheres, a gentle stream driven by stellar radiation. Some show clouds that flatten the spectrum, hiding deeper layers. So even in description, uncertainty is normal and calm. Now we touch the word habitable carefully. Habitable is not a promise. It is a range of conditions where liquid water could exist on a surface, given the right atmosphere. It depends on the star's brightness, the planet's distance, and the planet's air and reflectivity. Two planets in the same zone can be very different worlds. So we treat habitability as a clue, not a conclusion. Still, it matters because it guides where we listen more closely, and it expands the story from detection to possibility. Now let's add a quiet reminder about scale and perspective. Most stars are far away, and even the closest exoplanets are beyond any travel we can imagine soon. Yet, Their existence is not distant in a psychological way, because a tiny dip in light can carry a whole new world. A subtle wobble can reveal an unseen companion that has been orbiting for billions of years. This is the soft beauty of measurement. You can learn something real without touching it, and you can build confidence by using more than one method. For many systems, radial velocity and transits work together. The transit gives the size and the period. The wobble gives the mass estimate. Together, they give density, and density guides composition. If the wobble is absent or small, the planet might be low mass for its size. If the wobble is strong, the planet might be denser and heavier. Again, nothing needs to be dramatic. It is a slow layering of constraints. Now, let's briefly revisit the hot Jupiter surprise, because it teaches a quiet lesson about bias. Hot Jupiters are rare compared with smaller planets, but they are easy to find, so they dominated early discoveries. As the catalogs grew, the universe looked less like a row of Jupiters and more like a diverse garden. We discovered that multi-planet systems are common. We discovered resonances, where orbital periods form simple ratios. We discovered that planet formation is robust, happening in many environments. And we discovered that our solar system is one example, not a template. Now you can do a low stimulus check in your own mind. Which method feels most elegant to you? The wobble, the dip, or the lens? No need to answer out loud. Just notice which one feels like the cleanest idea. Now we place the recap sentence, slow and steady. Exoplanets are found by wobbles, dips, and lensing, effects on light and motion rather than direct pictures. And with enough precision, those effects can even hint at atmospheres and temperatures. Now we open the next loop, because each mystery adds a new sense for the universe. First, we measured stretched light and learned expansion. Then we measured a sky-wide glow and learned the afterglow of a hot beginning. Then we measured pulses and learned neutron stars spinning like lighthouses. Then we measured shadows and orbits and learned black holes. Then we measured motion and lensing and learned dark matter's hidden mass. Now we have measured tiny changes in starlight and learned there are worlds everywhere. So what comes next is a messenger even subtler than light. What if we could detect the stretching of space-time itself? Not by brightness, not by color, but by distance changes smaller than an atom's width. And what if that listening could hear black holes merging billions of light years away? That is where we go next. From worlds revealed by gentle dips, we turn to ripples in space-time and begin to listen. For the next 60 seconds, there are no new facts. Just a quiet permission to drift. We can measure the unseen gently by its effects. We can measure stretched light and learn that space is expanding. We can measure a sky-wide glow and learn the universe had a hotter beginning. We can measure steady pulses and learn a collapsed star can keep time. We can measure a shadow shaped by gravity and infer a black hole. We can measure motions that are too fast and infer extra mass in a halo. We can measure tiny dips in starlight and find hidden worlds. All of that is the same calm principle. We do not need to force the mind to hold every detail. We only need to trust the pattern. Affect, repeat, confirm. So take one slow breath and let the story carry you. In a moment, we will use that same principle in a new way, a measurement that does not depend on light at all. Now we turn to a kind of evidence that does not depend on light at all. It is a measurement of space-time itself, stretching and relaxing as waves pass. Gravitational waves were predicted long ago as a natural feature of general relativity. In that picture, gravity is not only a force, it is also the shape of space-time, gently curved by mass and energy. If the shape can curve, it can also ripple. Not like water rippling in water, but like distances rippling in space itself. A wave like this carries energy outward, away from whatever made it. It does not carry a color or a brightness. It carries a pattern of stretching, a change in separation between things. That is why it was so hard to detect, because the effect is unbelievably small, even when the source is immense. A passing wave changes distance by far less than the width of an atom. So the challenge was not only to build a detector, it was to build a detector that can tell a true signal from endless ordinary motion. Wind, trucks, ocean waves, tiny thermal jitters, all of it can move equipment. Even the ground itself is never perfectly still. So for decades, gravitational waves were a patient prediction waiting for patient engineering. What would count as proof had to be clear before anyone claimed success. It would need a distinctive pattern that matched theory, not a vague bump in noise. It would need careful calibration, so the instrument response was known and trusted. And it would need independent confirmation, the same pattern seen in more than one detector. That last part is soothing, because it protects us from fooling ourselves. A single instrument can have quirks. Two distant instruments agreeing is much harder to explain away. So the listening era began with a very specific kind of machine, an interferometer. If that word feels technical, keep only this image. A long, quiet hallway of light, split into two paths, then reunited. The detector begins with a stable laser, a steady source of light. The beam is split into two beams that travel down two long arms at right angles. Each beam reflects off mirrors and returns, over and over, building up its path length. Then the beams are brought back together. When they combine, they make an interference pattern, a gentle bright and dim signal. If both arms are exactly the same length, the pattern stays steady. If one arm becomes even slightly longer or shorter, the pattern shifts. So the detector turns a tiny change in distance into a measurable change in light. That is the calm trick. Measure distance changes by watching light interfere with itself. The arms have to be very long to make the effect easier to see. In the United States, the arms are several kilometers long. The light travels back and forth many times, increasing the effective distance. The mirrors are not ordinary mirrors. They are carefully shaped, carefully coated, and carefully suspended. Suspension matters because the mirrors must be isolated from ground motion. They hang like quiet pendulums which naturally filter out many vibrations. The light paths are inside vacuum tubes because air molecules would disturb the beam. The vacuum is kept extremely clean and stable. Temperature changes are managed because materials expand and contract with heat. Magnetic and electrical noise are monitored because they can nudge components. There are sensors everywhere, listening for disturbances that could mimic a signal. All of this is not to make the detector perfect. It is to make the detector understandable. When something appears in the data, the team must know whether it is from space or from Earth, so they inject test signals at times on purpose to verify the full pipeline. They calibrate the response by moving mirrors in controlled ways. They track the detector state continuously because reality is always shifting. This is what makes gravitational wave detection feel like quiet craftsmanship. Now, a soft curiosity question. Would you rather see a signal as a line on a graph or hear it as a sound? Both are translations of the same measured pattern. The wave is not literally audible in space, but its changing frequency can be mapped to audio so the human ear can notice structure. Still, the real proof is not in the sound. It is in the matched shape, the timing, and the statistics. So let's meet the first clear detection. In September of 2015, the detectors were newly improved and taking data. A short signal appeared, lasting only a fraction of a second. It rose in frequency and strength like a soft upward sweep. People call it a chirp because it climbs in pitch when translated to sound. In physical terms, it is two compact objects spiraling together faster and faster. As they orbit, they radiate gravitational waves, losing orbital energy. Losing energy makes them draw closer, which increases the orbital frequency. That rising frequency is the signature of an inspiral. Then comes a brief moment of merger when two become one. And after that, a ring down like a struck bell settling, but in curved spacetime. The remarkable part was not only the pattern, it was the fact that two detectors saw it. One detector is in Washington State, another is in Louisiana. They are separated by thousands of kilometers. The signal reached them at slightly different times, separated by only a few milliseconds. That tiny delay matches a wave traveling at the speed of light across Earth, and the waveform shape matched between the two sites. This is one of the strongest safeguards you can ask for. A local glitch would not naturally appear in both places with the right delay and matching form. The team then asked the next calm question: could random noise create something that looks like this? To answer, they estimated false alarm rates based on long stretches of data. They compared real coincidences to many time-shifted trials, a way to measure chance alignment. The result was that the event was extremely unlikely to be an accident, so the first detection became a measured fact, not a hopeful interpretation. What did the signal tell us? It pointed to a pair of black holes in a binary system. They were heavier than many black holes known from X-ray binaries at the time, and they merged, producing a final black hole and releasing energy as gravitational waves. This was a new kind of astronomy. Black holes merging do not need to shine in light for us to know they happened. They announce themselves by changing space-time. From the waveform, scientists inferred the masses and the distance within uncertainties. They also tested whether the signal matched general relativity's predictions in strong gravity. Within the sensitivity of the detectors, it matched well. That matters because it extends relativity's tests into a new regime. Not only gentle fields like the solar system, but intense, rapidly changing fields near merging black holes. The detection also solved a quieter puzzle. Do black holes form binaries that survive long enough to merge? The answer is yes, because the signal exists, and soon, many more signals were found, making the first one part of a population. With repeated detections, the field shifted from discovery to survey. The detectors began to compile catalogs of events. Each event is short, but together they map the life cycle of compact objects. Some are black hole pairs. Some are neutron star pairs. Some seem to be mixed pairs, a black hole with a neutron star companion. With each one, the analysis repeats the same careful steps. Check instrument status. Check environmental sensors. Compare detectors. Match to predicted waveforms. Estimate how often noise could mimic it. This is not a dramatic process. It is steady routine, designed to protect the truth of the measurement. Now we add a second milestone, because light eventually joined the listening. In August of 2017, a different kind of signal arrived. It lasted longer, because neutron stars are lighter than black holes and orbit longer in band. The waveform carried the signature of two neutron stars spiraling together. Again, the detectors saw it, and this time telescopes also found a fading glow in the sky afterward. This was the beginning of modern multi-messenger astronomy in a clear, shared way. Gravitational waves gave the time and a rough region of sky. Then many observatories searched that region for light. They found a transient source that changed over days, consistent with a kilonova. A kilonova is the light from material ejected in a neutron star merger heated by radioactive decay. We can say this calmly as measured signatures, not spectacle. The spectra and brightness evolution pointed to newly formed heavy elements. These are elements heavier than iron, produced by rapid neutron capture in extreme conditions. Gold and platinum are often mentioned as examples, though the full yield depends on details. The important point is not romance. It is that the data support a pathway for heavy element creation. This links a cosmic event to the periodic table in a quiet, measurable way. The neutron star merger also helped connect gravity waves to distances. Gravitational wave signals encode how far away the source is in a way similar to a standard candle. Because the amplitude falls with distance and the waveform shape helps break degeneracies. People call these sources standard sirens by analogy with standard candles. You do not need the phrase tonight. Just keep the idea that the wave itself contains a distance scale. If you can get a distance from the wave and a redshift from the light, you can measure cosmic expansion. This creates an independent route to the Hubble constant, separate from the traditional distance ladder. It is another way to cross-check the expansion story we began with earlier. So gravitational waves do not only confirm mergers, they also become tools for cosmology. Now, a gentle moment of perspective. For a century, Gravitational waves were mathematics waiting for measurement. Then, in a few years, measurement turned them into a new observational channel. It is like learning a new sense. Not a sharper eye, but a new way of feeling the universe's motion. And as the detectors improve, they will hear farther and more often. They will also localize sources better, making it easier for telescopes to join in. This is where the field becomes quietly powerful, because independent measurements can check each other. Light, neutrinos, and gravitational waves can each tell part of the same story. Now let's return to the interferometer with one more bedtime-friendly image. Imagine two long rulers made of light. A gravitational wave passes and one ruler lengthens while the other shortens, then they trade. The change is tiny, but the light interference makes it visible to the instrument. That is why the detectors are built as perpendicular arms. It makes them sensitive to the wave's stretching pattern. Different wave directions and polarizations change the response, which is why a network is valuable. More detectors across the world improve confidence and sky localization. So again, we see the theme of independent confirmation and consistency. What did this mystery solve? It solved that compact object mergers are real and not merely theoretical. It solved that general relativity's waveforms describe these events accurately within measurement limits. It solved that black holes exist not only as quiet masses, but as participants in dynamic pairings. It also opened a door, because each detection carries information about populations and formation channels. Are these black holes born from isolated binary stars, or from dense clusters, or both? The answer is likely a mixture, teased out by statistics and careful modeling. But for tonight, we stay with what is measured directly, the waves themselves. Now we connect gently to what comes next. Gravitational waves provide a new way to measure distances and expansion. And expansion has a surprising twist in the late universe. For a long time, people expected expansion to slow down under gravity. But faint, distant supernova measurements suggested the opposite. Expansion is speeding up. That is the mystery of dark energy, our next destination. Before we go there, let's place the recap sentence, slow and steady. Gravitational waves are direct measurements of space-time stretching detected with laser interferometers. They were confirmed by matching signals seen in independent detectors with patterns predicted by relativity. And when light joined in for a neutron-star merger, the universe became a multi-messenger story. Now we set the open loop clearly without tension. If expansion changes over time, waves and light can both help measure it. Standard candles and standard sirens can cross-check each other. So we return to expansion one more time with new tools and a new surprise. Next, we follow faint, distant light and learn why the universe seems to speed up instead of slowing down. When you are awake, comment one word so the next long video fits you. Write holes, matter, planets, or waves, and then let your attention rest. Now we meet a gentle surprise. The universe's stretching seems to be accelerating. Now we return to expansion, but with a gentle twist. For most of the 20th century, the intuitive expectation was simple. If matter attracts matter, then cosmic expansion should gradually slow down over time. The universe might still expand, but gravity should act like a quiet brake. So, the mystery is not whether expansion exists. The mystery is why the stretching appears to speed up instead of easing. To answer that, astronomers needed a reliable way to measure distance across deep cosmic time. Not a ruler in your hand, but a method that works for galaxies billions of light years away. Because the evidence must compare the near universe to the far universe, and far also means long ago. So we needed standard candles that can be seen at great distances. A standard candle is an object with a known intrinsic brightness, or one that can be corrected to a known brightness. If you know how bright it truly is, and you measure how bright it appears, you infer distance. The more distant it is, the dimmer it looks, in a predictable geometric way. This is the same calm logic we used for Cepeids earlier, but on a much larger stage. The key candle here is the Type 1, a supernova. Type 1 supernovae are powerful explosions of white dwarf stars in binary systems. They reach similar peak brightness, and with careful corrections, they become standardizable candles. Standardizable means not perfectly identical, but correctable using measured features of their light curves. In the 1990s, two large teams set out to measure distant Type 1 supernovae. Their goal was to learn whether the universe was decelerating, and if so, how much. They worked slowly and carefully because the stakes were high and the signals were faint. A distant supernova is a small temporary point of light among many steady points. You must find it at the right time, measure it repeatedly, and compare it to a calibrated system. Then you must correct for dust, which can dim and redden light in a way that mimics distance. You must also correct for selection effects, because surveys tend to notice the brightest events first. So the teams built guardrails. They used consistent photometry, cross-checked instruments, and compared many events rather than leaning on one. They checked host galaxy properties and looked for signs of extinction by dust. They improved their light curve fitting methods because the correction depends on the shape of the brightening and fading. All of this is the quiet scaffolding behind the headline result. Then the observation arrived, and it was not what the simplest expectation predicted. The distant supernovae appeared dimmer than expected in a universe that was slowing down. Dimmer here means farther than expected for their redshift. And farther at a given redshift means the universe expanded more than the decelerating models would allow. In other words, the expansion seems to have sped up during recent cosmic history. This was not a single point on a plot. It was a consistent offset across many supernovae with uncertainty bars carefully tracked. The conclusion was cautious at first, because extraordinary claims require calm checking, but the result persisted as more data came in. Different groups, different surveys, and improved calibrations continued to support the same basic finding. So the observational mystery became largely settled. The late universe is accelerating. Now we face the next question softly. If expansion accelerates, what could cause that? One simple possibility was already sitting in Einstein's equations, the cosmological constant. The cosmological constant behaves like an energy density associated with space itself. Unlike matter, it does not dilute in the same way as the universe expands. Matter thins out as volume grows, but a constant energy density per unit volume would remain, and so its total influence would grow as space grows. This can sound abstract, so keep a gentle image. Imagine space as having a very faint background pressure, not pushing like wind, but shaping the equations of expansion. As the universe grows larger and more dilute in matter, that background effect becomes comparatively more important. So the cosmic break weakens and the gentle push dominates. The phrase dark energy is often used for this accelerating component. But dark energy is a label, not a substance we have held in a container. It names the effect we infer from expansion history. The simplest model is that dark energy behaves like a cosmological constant, steady over time. More complex models allow it to vary, but the data so far fit well with something close to constant. There is a parameter people use called W, which relates pressure to energy density. To keep it bedtime gentle, think of W as describing the behavior of the component as the universe expands. For ordinary matter, the behavior is one way. For radiation, it is another. For a cosmological constant, W is near -1, a special value that leads to acceleration. You do not need to remember the number. Just remember that this is how scientists describe different expansion behaviors with a single calm quantity. Now we add the reassuring part. The acceleration is not supported only by supernova. Independent measurements connect to the same conclusion, reducing the chance of a single method illusion. One comes from baryon acoustic oscillations, the subtle ruler we mentioned earlier in the expansion story. Galaxy surveys measure a preferred clustering scale, an imprint stretched by expansion. By seeing how that scale appears at different redshifts, astronomers constrain the expansion history. Another comes from the cosmic microwave background. The background glow carries information about the universe's composition and geometry. When you combine cosmic microwave background constraints with baryon acoustic oscillation measurements, you get a consistent picture. That picture favors a universe with ordinary matter, dark matter, and a dominant accelerating component today. There is also the growth of structure as a cross-check. How quickly galaxies and clusters form depends on how fast the universe expands. Faster expansion makes it harder for gravity to build clumps because space is stretching more strongly. So measurements of clustering over time provide another way to test the expansion story. Again, you do not need the equations. You only need the calm idea that different datasets point to the same expansion history. Supernovae are one method, based on brightness and distance. Baryon acoustic oscillations are another, based on a statistical ruler. The cosmic microwave background is another, based on early universe patterns projected onto the sky. And together, they reduce ambiguity. Now we should also be honest, gently, about what is solved and what remains open. The observational conclusion that expansion accelerates is broadly accepted because multiple lines of evidence support it. But the physical cause is still being studied. Is it truly a cosmological constant, a property of space itself? Is it a new field that changes slowly over time? Or could gravity behave differently on the largest scales? These are active questions, and they can be held without tension. Uncertainty here is not a failure. It is a map of where measurement still has room to sharpen. Here is a quiet reflective prompt you can hold for a moment. Which is more soothing, knowing a mystery is solved or knowing exactly what remains unknown? Either answer is fine. Both are part of how science calms the mind, because it replaces vague worry with specific questions and measured constraints. Now let's make the acceleration feel intuitive without forcing a metaphor too hard. Imagine you roll a ball up a gentle hill. If nothing pushes, gravity slows it, and it eventually stops. That was the expectation for expansion. Slow down under gravity. But the supernova data suggests that, after a certain time, the slope changes. It is as if a very gentle tailwind begins to help the motion. Not a gust, not a shove, just a persistent, quiet effect that adds up over billions of years. This is why the acceleration was hard to notice for so long. It is not dramatic in a human lifetime. It is visible only when you compare enormous distances and long times. That is why supernovae were so important. They let us compare far and near with the same kind of candle. And it is why cross-checks matter. When several methods agree, the conclusion becomes more stable. Now we place a simple recap sentence to carry forward. The acceleration is supported by several independent measurements. The is it real mystery is largely settled. What remains is the deeper question of why, and that is still under study in a calm, careful way. With that, we have covered the main backbone of modern cosmology in this bedtime journey. Expansion, the afterglow, cosmic clocks, black holes, dark matter, exoplanets, and gravitational waves. Now we can enjoy two shorter mysteries that look intense from far away, but become calmer once their engines are identified. Next, we will visit quasars and gamma-ray bursts, beacons across time, and we will see how black holes and stellar death can explain them without leaving anything supernatural in the story. Before the next two mysteries, here is a soft glossary, just 3 calm terms. First, quasar. A quasar is a bright galactic center powered by matter falling into a supermassive black hole. The light comes from the hot, swirling disk around it, not from the black hole itself. Second, gamma-ray burst. A gamma-ray burst is a brief flash of very high-energy light from a catastrophic event far away. The burst is short, but it can be followed by softer light across hours and days. That brings us to the third word, afterglow. An afterglow is the fading light that follows, and it helps us locate the source and study what happened. If you like, say the 3 words silently once: quasar, gamma-ray burst, afterglow. Then let them go. With those words in place, we can treat these phenomena as signals with engines, not as chaos. Now we visit 2 phenomena that once looked like cosmic chaos but became calm once their engines were identified. These are beacons across time, quasars and gamma-ray bursts. They share a theme with everything tonight. A strange signal becomes ordinary when you can place it in distance, context, and mechanism. We will start with quasars because their mystery began as a simple mistake of scale. Early observers saw star-like points that did not look like galaxies at all. They were sharp, compact dots, some strong in radio waves, sitting among familiar stars. If you saw only their appearance, you might file them away as unusual stars. But spectra changed that story quietly and completely. When astronomers split their light into a spectrum, the lines did not sit where they should. The patterns looked familiar but shifted far from their usual positions. That shift was redshift, and it implied extreme distance. Extreme distance meant extreme brightness, far beyond what a single star could sustain. So the first puzzle was not only what they were, but how they could be that luminous. A second clue came from variability. Some of these objects brightened and dimmed over relatively short times. Short times matter because light cannot coordinate changes across a huge region instantly. If a source changes quickly, the region producing most of the light must be compact. So the clues pointed two ways at once. Far away, yet physically small. Far away means powerful, and small means concentrated. This combination is a signature you have heard before in a calmer form. It points to a compact engine fed by infalling matter. The solution was that these star-like points were actually the bright centers of distant galaxies. We now call them quasars, short for quasi-stellar sources, meaning star-like in appearance. Their power comes from accretion onto a supermassive black hole. The black hole itself does not shine. The light comes from hot gas in a disk, spiraling inward and heating as it loses energy. Near the center, temperatures rise, and the disk can glow across many wavelengths. Magnetic fields can also help launch jets, narrow streams that carry energy outward. Those jets can make the object bright in radio waves and can change the apparent brightness with orientation. So a quasar is not a random flare. It is a galaxy nucleus with a steady fuel supply, turning gravity into light with high efficiency. Once that engine was accepted, many other details began to fit. Broad emission lines made sense as fast-moving gas near the central region. Narrower lines could arise farther out, where gas moves more slowly. Absorption lines in between could come from gas clouds along the line of sight. Even the strange mix of brightness and compactness became natural. A small region can be immensely bright if the energy source is deep gravity rather than nuclear fusion alone. In a gentle way, quasars taught astronomers how energetic a galactic center can be. They also taught a practical lesson about distance. Because quasars are so bright, we can see them from very early epochs of cosmic history. They become backlights for the universe. Their light passes through intervening gas and galaxies before it reaches us. Along the way, it picks up absorption features like faint fingerprints stamped onto the beam. Those fingerprints let astronomers study the otherwise invisible material between galaxies. So quasars became tools as well as mysteries. Now we shift to gamma-ray bursts, which were almost the opposite kind of puzzle. Quasars shine for long times, like a distant city at night. Gamma-ray bursts appear suddenly, flash briefly, and then fade. Their discovery began in an unexpected place: military satellites monitoring the sky. In the late 1960s, satellites built to watch for nuclear tests detected brief gamma-ray flashes from space. At first, it was not clear whether the sources were near Earth within the solar system or far out in the galaxy. The bursts came from random directions, not concentrated along the plane of the Milky Way. That randomness hinted at great distance, but the evidence was incomplete. For years, the hardest problem was localization. A burst in gamma rays is hard to pinpoint precisely, because gamma ray detectors are not like ordinary cameras. Without a precise position, you cannot point optical telescopes to find the source afterward. So the mystery lingered, not because models were absent, but because the sky location was fuzzy. Then the key step arrived: afterglows. An afterglow is the fading light that follows the initial burst, often in X-rays, optical, and radio. Afterglows last longer than the burst itself, giving telescopes time to observe and measure positions accurately. Once afterglows were detected and localized, host galaxies could be identified. And once host galaxies were identified, distances could be measured through redshift. That single step turned the puzzle from speculation into classification. A crucial era came when satellites could trigger quickly and share coordinates fast enough for follow-up observations. Teams began to catch afterglows within hours, sometimes minutes, then watch them fade night by night. With redshifts in hand, the scale became clear. Gamma-ray bursts were not local fireworks. They were enormously energetic events in distant galaxies. But energy estimates also depend on beaming, because some bursts send energy in narrow jets rather than in all directions. So the engine had to be both powerful and efficient, and often collimated into a beam. Over time, a simple division emerged based on duration and spectral hardness. There are long gamma-ray bursts, lasting seconds to minutes, often with softer tails. And there are short gamma-ray bursts, typically under about 2 seconds, often harder in spectrum. This is not a perfect boundary, but it is a useful first map. The next question was what physical events could produce each class. For long bursts, evidence accumulated for a link to massive star collapse. Some long bursts were found in regions of active star formation, where massive stars are born and die. And in several cases, a supernova-like signature appeared in the afterglow light, strengthening the collapse connection. The picture that emerged is sometimes called a collapsar model. A massive star's core collapses, forming a black hole or a neutron star, while jets punch outward through the star. If a jet points toward Earth, we see a gamma-ray burst. The rest of the star can produce a bright supernova, and the fading afterglow traces the jet interacting with surrounding material. For short bursts, the locations and host galaxies often differed. Some short bursts were found in older stellar environments, not only in bright star-forming regions. That suggested a different origin, one not tied directly to the immediate death of a massive young star. The leading explanation became compact object mergers, like neutron star pairs or neutron stars merging with black holes. This is where our earlier gravitational wave story becomes a gentle helper. When gravitational waves and light were observed from a neutron star merger, it strengthened the merger pathway for at least some short bursts. It did not mean every short burst is identical, but it tightened the link between a class of bursts and a class of engines. Now we can say what solved looks like for these beacons. First, location. Precise positions on the sky, tied to host galaxies. Second, distance. Redshift measurements that place the event on the cosmic map. Third, engine, a physical model consistent with the timescales, energies, and environments observed. When those three pieces align, mystery becomes classification. And classification is calming, because it turns surprise into a predictable set of categories and causes. Quasars moved from star-like oddities to active galactic nuclei powered by accretion. Gamma-ray bursts moved from random flashes to distinct classes tied to collapse and mergers. Neither story ended curiosity, but both removed the feeling of cosmic randomness. Now, why do these beacons matter? Quietly, they are not only dramatic events, they are probes. Quasars illuminate the early universe, revealing the state of gas between galaxies through absorption features. They help us study how and when the universe became ionized after the first stars and galaxies formed. Gamma-ray bursts can also serve as backlights, especially at very high redshift, because they can be seen across great distances. They let us sample star formation and chemical enrichment in young galaxies long before our own solar system existed. Both phenomena also test physics under extreme conditions without needing to visit the event. We cannot approach a supermassive black hole's disk, but its spectrum carries a record of temperature and motion. We cannot stand beside a collapsing star, but the afterglow traces the interaction of jets with the surrounding medium, so the same calm method applies. Measure the effect, place it in context, and repeat across many cases. Here is a sleep-safe question you can hold for a moment. Do you prefer slow puzzles that take decades or fast puzzles that last seconds? Both get solved the same way, by careful measurement and patient cross-checking. If your mind is tired, let the details fade and keep only the spine. A beacon is only mysterious until we know its distance and its engine. Now we prepare to leave bright beacons and move to faint messengers. Some of the universe's most informative signals are not light at all. They are particles that pass through matter almost as if it is not there. Before we go, take the recap sentence, soft and steady. Quasars and gamma-ray bursts are now mapped to distances and engines, accretion and catastrophe, turning surprise into classification. And now we open the next loop, the one that leads to invisible particles and the early minutes of the universe. Next, we will meet neutrinos, faint messengers that can change identity on their journey to Earth. If you are still awake tomorrow, leave one word in the comments: light, motion, or time. It helps me shape the next calm documentary for you. Now we meet a gentle triumph, the almost undetectable neutrino. Now we meet a gentle triumph of an almost undetectable particle, the neutrino. Neutrinos are shy messengers. They pass through ordinary matter almost as if it is not there. Trillions stream through you each second, and you do not feel a thing. That quietness is exactly what makes them useful and challenging. They can escape from dense places where light cannot, carrying information outward. But because they interact so rarely, detecting them requires patience and careful design. Our first neutrino mystery is called the solar neutrino problem. It sounds dramatic, but it was a calm, persistent mismatch. The sun is powered by nuclear fusion in its core. In fusion reactions, neutrinos are produced in large numbers. Solar models predicted how many neutrinos should reach Earth. Then experiments tried to count them, and they found a deficit. Fewer neutrinos were detected than theory expected. That matters because it creates a fork in the road. Either our understanding of the sun's core was wrong, or our understanding of neutrinos was incomplete. Both possibilities were important, and neither was comfortable to accept too quickly. So the field moved slowly, adding measurements rather than arguments. The earliest famous measurements used a large underground detector filled with cleaning fluid. It captured a tiny number of neutrino interactions, patiently, over years. The result consistently came out low, about a third to a half of the expected value depending on details. At first, it was easy to suspect the detector. Maybe the chemistry was off. Maybe backgrounds were fooling the count. Maybe the theory was too confident. So other experiments joined in with different technologies. Some used gallium to be sensitive to lower energy solar neutrinos. Some used water to detect a different interaction signature. Each one had different systematics and different strengths. The important point is not the materials. It is the logic. Multiple detector types reduce the chance of a single instrument mistake, and the deficit persisted across them. That persistence shifted the problem from a local concern to a real puzzle. Meanwhile, solar physics improved too. Helioseismology, the study of sound waves inside the sun, tested solar structure independently. Those tests supported the basic solar model of temperature and density profiles. So the sun looked increasingly correct. That nudged attention toward the neutrino side of the fork. Now we reach the solution, and it is quietly elegant. Neutrinos can change identity in flight. They come in three types, often called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Solar fusion primarily produces electron neutrinos. Early detectors were most sensitive to electron neutrinos. So if neutrinos changed flavor on the way to Earth, the count would drop even if the total number stayed the same. This is the core idea of neutrino oscillations. Oscillations means the neutrino is not locked into one flavor forever. It can transform as it travels, like a slow rhythm between identities. That seems strange until you learn what it implies. It implies neutrinos have mass. Not a large mass, but a small, real mass. If neutrinos were exactly massless, the simplest form of oscillation would not occur. So the solar neutrino deficit became evidence that the standard particle picture needed a gentle update. Confirming this required experiments that could see more than one flavor. A key step came from detectors that used heavy water, which allowed multiple interaction channels. One channel was sensitive mainly to electron neutrinos. Another channel counted all neutrino flavors more equally. When those measurements were compared, something beautiful happened. The electron neutrino count was low, but the total neutrino count matched solar predictions, so the sun was producing the expected number of neutrinos. They were simply arriving in a different mix of flavors than they started with. Another strong confirmation came from atmospheric neutrinos produced when cosmic rays strike Earth's atmosphere. Those neutrinos showed flavor changes that depended on the path length through Earth. More change for neutrinos that traveled farther. This fit the oscillation picture again, with a different source and different energies. So two separate natural laboratories, the sun and the atmosphere, pointed to the same behavior. The solar neutrino problem did not vanish by hand-waving. It clicked into place through converging measurements. Now the solution can be said in one calm sentence. The sun makes the predicted neutrinos, and neutrinos change flavor on the way to us. And the deeper implication is another sentence. Neutrinos have a small but real mass, which extends the standard model of particle physics. This kind of solve is soothing. It does not make the universe simpler. It makes it more coherent. It aligns two fields, stellar physics and particle physics, without forcing either to break. Now we move to the second puzzle in this bonus pair, about the early universe. This one is not about particles changing identity, but about the first few minutes after the hot beginning. If the universe began hot and dense, then early on it was a nuclear reactor spread through space. In those early minutes, protons and neutrons combined to form light nuclei. This process is called Big Bang nucleosynthesis. It is a testable calculation. Given the density of ordinary matter and the expansion rate, the theory predicts how much helium, deuterium, and a little lithium should form. Most hydrogen remains hydrogen. A significant fraction becomes helium. A tiny fraction becomes deuterium and helium-3. And there is a small amount of lithium-7 predicted as well. These predicted abundances act like a fossil record, because later stars can make and destroy elements, but the primordial pattern leaves a baseline. Astronomers look for environments that preserve early abundances as well as possible. For deuterium, they often use absorption features in distant gas clouds seen against bright background sources. For helium, they examine low metallicity regions where stellar processing is minimal. The details can be complex, so tonight we keep the spine. The key is that observations of light element abundances can be compared to a calculation from the first minutes. For many years, this comparison supported a hot early phase strongly. Then something even more reassuring happened. The cosmic microwave background, measured much later, provides an independent estimate of the density of ordinary matter. And that estimate agrees well with what Big Bang nucleosynthesis requires to match observed deuterium and helium. So we get a calm convergence between two fossils. One fossil is the afterglow of early light. Another fossil is the chemistry of light elements. They point to the same storyline, an early hot universe that cooled as it expanded. This is the kind of cross-check that turns a narrative into a coherent picture. Now, we also include a quiet note about what remains imperfect. There is a known tension involving lithium. The simplest Big Bang nucleosynthesis calculations tend to predict more lithium than is observed in some old stars. This is called the lithium problem. We do not turn it into suspense tonight. It may involve stellar physics that depletes lithium in star atmospheres or refinements in nuclear rates or other effects. The important point is that a single tension does not erase the overall convergence. Most of the light element story fits well, and the mismatch is a focused clue for further work. Now we widen to the idea of convergence across the universe's timeline. We have several ways to estimate the universe's age and history. Expansion measurements, combined with cosmic microwave background constraints, give an age estimate. Stellar populations, like the ages of the oldest star clusters, provide another kind of clock. The growth of structure and the distribution of galaxies provide additional constraints. These methods are not identical. They rely on different data and different assumptions, yet they converge on a consistent timeline within uncertainties, which is soothing. It means we are not balancing on one fragile method. We are building a story supported by multiple independent clocks. So in this section, two puzzles clicked in a similar way. The solar neutrino problem was solved when detectors could measure flavors and confirm oscillations. The early universe minutes were confirmed when observed light element abundances matched calculations and agreed with cosmic microwave background inferred baryon density. Both are examples of invisible messengers turning into measurements. Neutrinos are invisible to our eyes, but detectable with enormous patience. Primordial chemistry is invisible as an event, but readable as a leftover pattern. Now we connect these results back to the larger arc of the video. Neutrino physics links to the Standard Model and to how stars shine. Big Bang nucleosynthesis links to the hot beginning implied by the cosmic microwave background. Both support the idea that the universe's history can be reconstructed from quiet leftovers. Now we place the recap sentence, slow and steady. Neutrino oscillations solved the solar deficit, and light element abundances confirmed an early hot phase. And we close the open loop gently. These results connect back to expansion and the cosmic microwave background as one coherent picture. You do not need to remember every detail. Listen for the one-sentence closures as we move toward the end. Next, we will do a final, slow recap that revisits each solved mystery in a single sentence, so your mind can stop searching for what it might have missed. If you want more 2-hour science nights like this, subscribe, so the next one arrives without you searching. Now we do a gentle recap like tidying a desk, one solved mystery at a time. Now we close the loops, slowly, one sentence per mystery. You do not need to hold every detail. Just let each sentence pass through like a calm tide. First, expansion. Across many galaxies, distance and redshift rise together, showing that space itself is stretching over time. Second, the cosmic microwave background. Across the whole sky, we measure a near-uniform microwave glow with a thermal spectrum, the cooled afterglow of a hotter beginning. Third, pulsars. Pulsars are rotating neutron stars, identified by repeatable timing and by their place in supernova remnants and binary systems. Fourth, black holes. Black holes are compact masses confirmed by orbital dynamics, by the light of infalling matter, and now by shadow-like imaging near the horizon. Fifth, dark matter. Dark matter is extra-gravitating mass required by galaxy motions, by gravitational lensing maps, and by early universe patterns that fit best with a non-luminous component. Sixth, exoplanets. Exoplanets are unseen worlds found by a star's subtle wobble, by tiny repeated dips in starlight, and sometimes by lensing or timing effects. Seventh, gravitational waves. Gravitational waves are direct measurements of space-time ripples, detected with laser interferometers and confirmed through matching signals in independent detectors. Eighth, dark energy. Dark energy is the name we give to the observed acceleration of expansion, supported by distant supernova distances and by independent cosmic rulers that agree on the same history. That is the whole arc, reduced to 8 gentle closures. Each one began as a question. Each one became a clue, then a measurement, then a calm consensus, and now nothing you need to do. If a thought returns, you can place it on one word. Measured. Measured. Let the word be a small weight that lowers the mind back into the bed. Measured means checked. Measured means repeated. Measured means the universe left notes we could read without rushing. If you drifted in and out, that is fine. This story is built to loop quietly, with structure that does not demand attention. Every future episode here will follow the same calm pattern. A question, a clue, a breakthrough, and a soft recap you can keep or let go. Measured. And now we pause for a few slow breaths. Inhale gently. Exhale slowly. Inhale as if you are listening from far away. Exhale and let the room stay the same. If you are still awake, you do not need to decide anything. If you are sleepy, you do not need to fight it. Measured. And now, we will finish with a final brief closing, and then we will let the night remain quiet. If you would like more long, calm science nights, subscribe so the next story arrives without you searching. When you are awake, comment one word to choose the next bedtime topic: oceans, stars, or time. Thank you for listening, and good night.